And yeah, thank you very much for the introduction. And here we are counting. Why am I not in the counting session? Well, counting session was about counting queries, queries that count answers. Whereas here we will be concerned with counting constructors. And so in the earlier literature, extensions of ALC with counting constructors have been considered. And in particular, comparisons with respect to fixed natural numbers have been considered. So if we take into account the local level or what we can count about individuals, well, the most prominent constructor has been for sure qualified number restrictions, where we compare the number of our successors in C of a given individual with respect to a natural number. For ALCQ, the extension of ALC with these constructors, the problem of concept satisfiability has been shown to be p-space complete without t-box and x-time complete in case we add some knowledge base in form of a t-box. On the global level, on the other hand, cardinality restrictions have been introduced in earlier literature by Franz and co-authors. And in particular, they decide to add constructors that act on the entire interpretation and try to compare the cardinality of a concept with respect, again, to a fixed natural number. For such an addition, complexity is a bit higher, a bit harder, and depends also on the encoding of numbers. In 2000, Tobias showed that with binary coding of numbers, consistency with respect to C boxes in ALCQ is next time complete. So to give an example of how this constructor works, we have a network. You can imagine a Zoom session with a centralized server. And here I am, like I am D0 and I am connected. Let's imagine that I'm connected to at least 2 peers. So I'm sort of in a good shape. I have some redundancy, and in particular, I have at least 2 online links. And we can also say that the entire network, or I, is not dead because we do not have like all online or all offline links. In particular, here we say that there is at least 1 offline link. The question that I would like to analyze in this talk is what we can really count using these constructors, what we cannot, and at what cost. Is it going to be harder to count more than this? Well, let's start with some preliminaries. The extensions that we will investigate in this talk are quite recent. In particular, we will have a look at an infinite variant of what's called QF-BAPA, which stands for the quantifier-free Boolean algebra with Pressburger arithmetics. And for this mouthful, what we mean is actually just a Boolean combination of comparisons between positive linear combinations of set cardinalities. How we evaluate cardinalities? Well, we add an infinity, which stands for all sort of infinite cardinals. So we collapse them and we just say they are infinite. And we define a semantics in terms of substitutions. We assign to set variables subset of the universe, which we denote with this calligraphic U. Again, an example of how semantics works in this context is given here. We can somehow see that now we talk about flat interpretations. We have no links between nodes, and possible constraints that we can define here is, for instance, the constraint of a network that's not doing very well because online links, online peers are less or at most equal to the offline ones, or an odd network, which is of course not the case, because to satisfy the second constraint, we would need the universe to be infinite. In a paper from last year, we showed that formula satisfiability in this small logic alone without the DL setting is NP complete, in spite of the fact that we had a lot of non-determinism by having Boolean operators on the set level, on the formula level, and of course solvability over the naturals, we are able to stay in MP. So now, how do we apply this to description logic? Well, first, on the local level, we define the description logic ALC SEC infinity, which stands for ALC extended with a role successor constructor that allows us to specify constraints over role successors using QF-BAPA infinity. And the semantics is given by defining the universe as the set of all role successors of an individual, and then, well, the roles are the role symbols or the set variables are interpreted as the R successors of a given individual, and concepts are restricted to the set universe. And we say that an individual satisfies a constraint if and only if the induced QF-BAPA infinity substitution satisfies such a constraint. So, for instance, if we had a T-box where we say that a good network is one that has at least as many online links as offline ones, then we would say that in our example, the blue dot, which would be our instance of a good network, actually does not satisfy the T-box. So this would be a counterexample, if you will. And we already defined for ease of notation and also for analysis some sublogics. Well, we could say that ALCQ is actually the restriction of ALC SEC infinity to a very particular shape where we only have role intersected concept compared to a natural number. We define ALC CQU, which is the restriction where we only allow a linear combination of set cardinalities on the left-hand side. And we define ALCQT, which is similar to ALCQ, except that we do not have role names, but we have safe role types. So we take the entire role signature and we partition it using sort of a Venn diagram. I hope the illustration on the right helps you visualizing what I mean by safe role type. On the global level, we introduce in this paper, or let's say the paper that we then abstracted and summarized, we introduce a generalization of cardinality restriction and concept inclusions in the form of extended cardinality restrictions, which are nothing else than QF-BAPA infinity formulae that have as variables concept descriptions. We refer to as a EC box to a Boolean combination of such restrictions. And we define also RC boxes. RC boxes are essentially conjunctions of such extended restrictions where we disallow constants. So we can only have multiples of set cardinalities, but no additional constant term. And you can think of one of previous examples indeed as an RC box. Again, for ease of notation, we also introduce Boolean T boxes and C boxes. We just say, okay, we take concept inclusion or restrictions, and we take Boolean combinations of that. It has to be noticed that indeed, for superlogics of ALC, EC boxes or extended cardinality restrictions actually generalize both concept inclusions and CRs. In particular, here I showed how we can generalize a CI. So now we had some preliminaries. We can talk about the complexity, about how is it harder, if it is, to use these extensions. Well, it turns out that actually there's not much more to it. We stay in the same complexity class with respect to concept satisfiability if we compare to ALCQ. And if we jump to the global level, we can see in this quite informative table that we keep for C boxes and EC boxes the same complexity. We have non-deterministic exponential time. And for RC boxes, we actually are able to jump down, take one step back, and go to the level of T boxes in all the languages that we consider. So now that we've seen that adding such constraints does not add to the complexity, our next question is, do they actually increase the expressive power? Or is it just syntactic sugar? Well, let's focus first on the local level. In last year's paper, we showed that ALC CQU, where we only have linear combinations on the left and constants on the right, we already jump a bit with expressivity. We're more expressive than ALCQ. The tool that we use is counting by simulation, which is a bisimulation defined by Lutz, Baader, and Volter that actually characterizes ALCQ concepts as the first order fragment that is invariant under such a bisimulation. Maybe not so surprisingly, we show that ALCCQU and ALCQT are equivalent. Well, the inclusion in on one direction is rather easy, from ALCQT to ALCCQU. The other is not as trivial. It is actually double exponential, but it is just a matter of encoding. If we then go to the reasoning side, they stay the same complexity. And now we define a notion of bisimulation for ALCQT, or at this point for ALCCQU, since they are equivalent, that generalizes the counting bisimulation by replacing role names with safe role types. What we show is that actually ALCQT and ALCCQU as well is characterized by this bisimulation. It is indeed the fragment of first order formulae in one free variable that is invariant under such bisimulation. But we also notice that all ALC-SEC infinity is invariant. What turns out is that actually we can give a proper semantic characterization of ALC-CQU as the first order fragment of ALC-SEC infinity. On the right-hand side, you can see in a visualized and graphical way this expressivity lattice, if you will, where ALCQ stands on the bottom, then we jump a bit with ALCQT and ALCCQ, and then we jump to the top with ALC-SEC infinity. So the novel contribution, if you will, of this paper is that we also had a study on the global level. First, I will focus on T-boxes. And the idea here is that we take our bisimulation and we globalize it, which means that essentially two interpretations are now bisimilar if there is a bisimulation that spans over both interpretations entirely. What we showed here is that Boolean CCQU T-boxes are invariant under such a bisimulation. And in particular, if we add the additional condition of being invariant under disjoint unions, which is a property enjoyed by T-boxes and not by Boolean T-boxes, we're able to characterize ALCCQ T-boxes as first-order sentences that are invariant under the global bisimulation and disjoint unions. And using a similar line of reasoning as for the local case, we showed that first-order definable ALC-SEC infinity T-boxes are indeed equivalent to LCCQU T-boxes. And there we also managed to strictly separate ALC-SEC infinity and ALCCQU T-boxes. The proof is a bit rough. It is unelegant. We had to fiddle a bit with this, but we showed that the GCI, where we compare as an equality cardinalities of a row successor with respect to A and not A, is not first order definable. Now that we looked at T-boxes, let's jump to the last interesting bit, which is counting boxes. And the idea here is that we take bisimulations and we combine them with first order counting games. So we take the so-called notion of comparative LCQT bisimulation, where we actually ask that no matter what finite set, subset of the interpretation we take, we are always able to jump on the other interpretation and find the set that is in bijection with respect to the bisimulation. The first theorem
just a note, you have 1 minute.
Yes, I will go quickly. So we proved that actually interpretation related by bisimulation satisfy equality of cardinalities for all concepts. And in a similar fashion, we proved some characterization results. Last slide will contain a nice lattice that shows this. Here, again, we proved what is first order definable. And for the last case, we actually managed to separate first order from not first order using a very elegant tool called 0-1 laws for first order logic, where basically we say that every first order sentence for which we define this function has a limit that converges to 0 to 1. And we show that for such an easy box, this is not the case, hence non-expressibility. So this is the final lattice for expressivity results on the global level. We separated first order fragments and then found some more. And for the future, we set up some sequels. So what can and cannot these description logics count in the finite if we remove infinity for Q papa? And can we count efficiently? Well, this is what I'm looking into right now. Thank you for the attention.